Welcome to ViWA, the Virtual Water Values Project of GRoW. I have the pleasure to introduce to you for the next few minutes highlights from the project. If you want to learn more about it, we have a marketplace that will stay forever, longer than this conference, where you can get your information from the different projects. And we also have a side event on Friday, October 23 at 10 a.m. Central European Summertime. And there we will explain to you what we have found out about global to local and local to global. Now, the science issues of ViWA. Agriculture is, and agricultural water use is at the center of ViWA. And agriculture uses 92% or even more of green and blue water in the form of rainwater and irrigation. As Mr. Unba has pointed out in his very interesting talk, and very informative talk that we just heard, most of this is wasteful, and it withholds water from natural ecosystems and human use without any gain for both. We don't profit anything from this waste. So monitoring and improving agricultural water use efficiency contributes to the SDGs 2 and 6, and this is where we want to contribute to also with our projects. Now, if you look at the yield and the water use efficiency in kilogram of yield per cubic meter of water that is evaporated into the atmosphere, you see that there is a relationship between the two. And if you look at very low yields, that means very inefficient agriculture, you also, this is connected with very low agricultural water use efficiency. This is where you waste water. If you intensify agriculture, not beyond the point of sustainable agriculture, hopefully, you increase water use efficiency. And this is where we have a win-win situation for both the food security and the non-wasteful water use. So sustainable development postulates that natural resources like water be used with the highest possible sustainable efficiency. And that's not only locally, but also globally and regionally. So our question that we ask in ViWA is not so much how much virtual water is used by agriculture, but how can water use in agriculture become more efficient and sustainable? We have three goals, three research goals that I want to introduce to you, three highlights, and they are along the issue of improving practical understanding of efficiency and sustainability in agricultural water use on all scales from local to global. So the first one I want to address is how can the agricultural water use efficiency be monitored globally and regionally using big environmental data, and that informs water, food, energy simulations. Now we have sophisticated crop growth simulation models that are informed by satellite observations that you can see to the right, where you have these red dots on the globe, where we have samples of satellite images, each 100 by 100 kilometers, where we can virtually look at each single field. And this is the new satellite images that come from the EU Copernicus data streams. And we process this big environmental data. 15,000 of these Sentinel-2 images have been processed in the project and analyzed to get information of the actual growth conditions of agriculture. And we put this information into a high-performance environmental computing environment where we simulate globally at 1 kilometer resolution and 1 hour the water use efficiency and the yields that come out at the end of the day. Now, what is the result? The result is a global agriculture water use efficiency monitor, which monitors actually the water use efficiency. Here, as an example for maize, we have 16 other crops that we are observing and monitoring, where you can see that there are different water use efficiencies. When you grow maize, you have hotspots of water waste in sub-Saharan Africa, but also in Mexico, but you have also cold spots in the US and in southern China, where water is already used very efficiently. All this will be provided as results on the food security thematic exploitation platform network, where everybody can have access to this data. Now, the next thing I want to highlight, I want to point out is how can we use this monitor and how can we use the water use efficiency and how can improvements in water use efficiency best be incentivized through its consideration in ecological economic analyses of water use and food trade scenarios. For this, we use a computable general equilibrium simulation model that can simulate policy impacts. Here we have pricing of irrigation water as a policy impact. We use the ART model of the Kiel Institute for the World Economy that has been developed specifically for this project. And if you have a scenario of introducing water pricing for agriculture globally on all agricultural land and crops, you see that, for example, if you look at maize and soybean, the irrigated soybean, which is black, and the irrigated maize, which is green, it goes down in supply, the production goes down, the rain fed goes up, but not in the same to the same amount. And that's the same in the Mediterranean, a sharp reduction in irrigated maize and not so sharp decline in rain-fed maize. So what this means is that there is a change in trade balance of maize, and you can see that the Mediterranean in this case becomes an importer, and the US and Brazil become exporters, even more so if you apply the irrigation shock. With this instrument, we can now play through different scenarios and see what the best incentivification is for reaching a more sustainable use of agricultural water. Third point, how can regional water, food, energy conflicts be analyzed and negative ecological impacts be assessed? Now we go from the local to the regional, from the global to the regional and local, and we analyze the water, food, energy conflicts and their ecological consequences in large transnational basins like the Danube and the Zambezi. You have the water, the rainfall, that is used to produce food, and that is turned into virtual water that is consumed and then transpired into the atmosphere. So this is what produces food and goes to the global and local food markets. You have water that also goes downstream, with which you can produce hydropower. And you have, with all these things, you have ecological implications and negative ecological effects. So you create water conflicts. I will demonstrate you a use case of these water conflicts and how we analyze them. It's the expansion of irrigation in the Danube Basin. The Danube Basin is a large multinational, international, actually the most international large basin on the globe. We look at the case of maize. The lower Danube countries push for expansion of irrigation. There is currently a World Bank study going on that is looking into this, and the International Commission for the Protection of the Danube River already uses our simulations and the results of our simulations to inform the ministries of the different countries within workshops where we participate. So, taking maize as an example, what is the actual situation? The actual situation that we simulate is not only water, but also coupled in the same model, the actual plant growth and the yield. So what we model is something like 7 tons per hectare of yield in the region. Very diversified yield. You have intensive and less intensive agriculture. And we model the mean water use efficiency of maize, which is 1.8 kilograms per cubic meter. And at the same time, we conduct an ecological sustainability assessment with indicators that we have developed in very high resolution. And you see that here the environmental flow requirements are displayed in August, for example, and 41% of the rivers already now have unsustainable flows during the summertime. Now, this is very high resolution, and you can see here how you can get information on each upstream river on the ecological sustainability indicators and go very, very locally into the very single point. Now, if you switch on irrigation, if large-scale irrigation is introduced, you see that the yield is almost doubling. This increases the production to almost twice as much, but the price is 29 gigacubic meters of water that is extracted from the rivers or from the water system and is pumped into maize. So the maize water use efficiency is increasing. So water is used with a higher efficiency. And you can see this in many areas like Hungary here or Romania here, where the water use efficiency increases, which is a good signal on the other hand. Now, this has implications on the flow regimes and on the rivers. And you can see here the river network of the Danube, and you can see here the monthly runoff of the different locations. Blue is without irrigation, red is with irrigation. If you look at it upstream in Germany, in Bavaria, you almost have no irrigation. There is enough water. And if you go more downstream, you see that even in July, you have situations here in lower Romania where almost all the water that is flowing in the river is consumed for irrigation. So this is very severe implications on it, and this is all simulated in a water, food, energy analysis and ecology analysis. And you can see now how this irrigation changes the situation, so that we now have more than 4% of the rivers that have negative flows, where more water is extracted and there is a flow in August. So this is severe, and this shows the consequences of this kind of scenario. A regional water, food, energy ecosystems assessment, again, of this one scenario that I present to you now is we have a huge amount of water that is extracted in Hungary and Romania. Mainly, we have maize production, which is doubled roughly, which increases the volume of sales of maize by about 6 billion euros per year. We have a reduction of hydropower production, which is equivalent to a decrease of volume of sales of approximately 30 million euros per year. So now you see there is a factor of 100 between those two. But there is also, and this is even more important, severe impacts of introducing irrigation of maize on almost all rivers in the lower Danube. More than 50% of the wetlands are negatively affected. So this has to be taken into account by the decision makers. But you can now look from all different sides on this issue of more irrigation in the Danube Basin as an example. Now, our achievements as a final slide. We have a global water use efficiency monitor up and running. It will roll out on the food security tab with all its results very soon. The spin-off of this is that a early European yield forecast system was developed by Vista GmbH, which is a partner in the project and is now available for commercial and used already commercially to get a very early and accurate picture of the expected yields of different crops in Europe. The general computable equilibrium model ART for the first time incorporates agricultural water, the blue and green water, in the evaluation of scenarios for moving towards a more sustainable water use in agriculture and industry by taking into account global commodity trade. New tools were developed for regional water, food, energy, ecology assessment, as I showed in the Danube, and they were successfully implemented and tested. And the regional ICPDR workshops are now conducted together with ViWA to inform Danube countries' ministries about the impact of irrigation and to give them hands-on information of what may happen in the future and how they can make better decisions. The water governance assessment tool is improving management of water shortage challenges and, of course, their governance. With this, I thank you very much. As I showed you, there is a website where you can visit us and where you can also look at the different partners, which I don't have, unfortunately, time enough to introduce in detail. Thank you very much.